right. So let me read this to you guys out loud. It says an aluminum tape measurer is accurate at 20 degrees Celsius. And so then what happens if you put it in a freezer and you go from 20 degrees to, what is it, 5 degrees Celsius? What does it say? Yeah. What would it do? Would it read high or low? And then what would the percentage error be? And so what we want to look for is this is our ruler. And just pretend it's like an aluminum ruler. That means it's made out of metal. And it's accurate at 20 degrees Celsius. So that's like our first temperature. And then our second temperature is negative 5 degrees Celsius. So let's just think conceptually before we start throwing a bunch of formulas and trying to calculate it. What's this thing going to do conceptually when I put it in the freezer? Everybody's doing this hand thing. It's going to contract. It's going to shrink. So if they want a percentage, we need to calculate some numbers. Okay? This is section 10.4. So what I'd like for you to do, if you have your book open, I want you to turn to page 379. And it's thermal expansion of solids. And there is one equation that we're going to use on page 379. And I want you to guess what that equation is. Take a guess. Somebody say it if you know it.
Is it delta L over L naught plus alpha delta T?
All right, absolutely correct. That's the formula that we're going to use. Now, Mr. Adams is a physics teacher, so I've memorized what all those things mean. But what does delta L represent? Change. Anything with delta represents change, so that's the change in length. What does L naught represent?
The initial length.
What is delta T?
The change in temperature.
Good. What is alpha? Who remembers that?
Alpha is a constant depending on the material.
Yeah, alpha is the constant, and we call it the constant coefficient of thermal expansion, and it's based on the material. What kind of material was this ruler made out of?
Aluminum.
Aluminum. So this is an aluminum. Did I spell that right? I think I did. All right. So if we convert this to Kelvin, what do I do to convert 20 degrees Celsius to Kelvin?
You would add 270.
Add 270. So this is really 293 degrees Kelvin, right? What is this? What is minus 5 degrees if you add 273 to it?
268.
Huh? I heard it.
268.
268. So let's start doing some math here, and we'll come back to it. Delta T is 293. Well, actually, delta T is the final temperature, which is minus 263. Whoops. Let me put this back down. Oops. Is actually 268 minus 293. Right? Does that seem right to you guys? Oh no, it's a positive 268. Okay. I'm trying to do the Celsius and everything together. So what's that equal? Negative 25. Hey, by the way, here's a little thing you guys may not be aware of. If I left that in Celsius and I'm calculating delta T, what would the difference be in Celsius? You go from 20 to negative 5. Same thing.
Same thing.
That doesn't work. Same but different. Yeah. That doesn't work for Fahrenheit though. It only works for Celsius. Alright, so what else do we need? Well, that's what we're going to calculate, but before I can calculate the length, don't I need to know this coefficient of aluminum, right? So in your textbook, and this should be in your notes if you wrote it down, but I said you don't need to write it down because it's in your book. But on page 369, you can actually find the alpha for aluminum. And alpha is the thermal expansion coefficient. And for aluminum, it is 24 times 10 to the negative 6. So this is 24 times 10, and we'll make that a little smaller there, times 10 to the negative 6. So if I want to find delta L over L, then I'm going to say 24 times 10 to the negative 6, right, times negative 25 degrees Kelvin. Guess what that is? Well, if we plug that in our calculator, we get delta L is equal to negative 0.0, well, it's a bunch of zeros, but it ends up becoming like negative 6.0 times 10 to the negative 4, I think, if I do the math. Right? Now, if you convert that to a percentage, you get delta L over L is equal to 0.06%, I think. Right? Now, what Mr. Adams, somebody said, Mr. Adams, so this is the part B part, right? Part A was, will it read high or will it read low? And we said that it will read high because the ruler literally shrinks, which means that 12 inches, when you measure 12 inches, it's not quite 12 inches. So whatever you measure will be actually, it'll measure higher. In other words, the numbers will be higher because you're taking that standardized measurement and shrinking it so you can fit more of those smaller rulers in there. Okay? So that was part A. Part B said that the air, the standard air. Remember that in science, to calculate the standard air, you're going to have, and this is like L naught, your original length. You take your original, or sometimes the theoretical, but in this case we'll take the original, and then it's usually going to be the final minus the original, which is a fancy way of saying delta L. And depending if you're doing like theoretical versus empirical, it's the same thing. You're going to take the theoretical minus the empirical all over the theoretical. And then there's observations too. So, but basically it's delta L over delta naught, or not delta naught, it's delta whatever over whatever. Does that make sense to you guys? How much of a percentage error is that? Is that something to be worried about? No, not if you're building a house or building something small. What if Mr. Adams was, is this the best way to measure the distance to the moon?
What if you were building a bridge?
Would you want your family, would you drive your family?
That's a great question, I'm gonna leave it in the video. The question was, what if you're building a bridge? Would it matter then? In other words, and we got a bridge here, what if it was like, what's the longest bridge you guys can think of that's made out of metal?
Mackinac Bridge.
Mackinac, we're in Michigan, Mackinac's a pretty large bridge.
Golden Gate,
Golden Gate's another one. Do you think they think about this?
yes.
Absolutely, the engineers can calculate this. In fact, they have to make sure that they accommodate for the expansion and the contraction of the metals that are used in the bridge as the concrete and all those other things. So absolutely, they don't just go out and measure and say, I need a steel beam that's 20 feet long. They say, I need a steel beam, and we need to attach the steel beams in such a way that they're able to expand plus or minus whatever the air is, or whatever the thermal expansion allows for. That's why when you drive down the highway, like I-94, you don't realize it, but there are 1 to 2 inch gaps in the cement slabs, and those allow for it. That's why when you drive down the highway, you hear your tires go dum dum dum. When you're going 70 miles an hour and you go over those little gaps, it's a very small minor thing. Most people don't notice it, but what they do is they put little gaps in the cement slabs so that when it's hot in the summertime, as the cement expands, there aren't these big huge bumps that come up in the middle of the road. And there's also some room, I know I said it funny, we're just trying to live. And then when it gets really cold in the winter, because in Michigan, we could go from like -10 to like 80 degrees in one day, right, in Michigan. So we really have to be aware of that, all right? And that's why try it when you drive on the highway, that's where you see it the most. And there's a lot of work and engineering that goes into that, okay?